Hello and welcome to this video. We're going to be covering the basic functionalities of the digital software. And digital essentially is just sort of like LT-Spice, but just for digital circuits. So the first step you want to do is download it. So because it's Java based, it can run on any platform. As you can see here, I am on Linux, but it works on Windows and Mac. Fair bit of warning about the Mac version though. It won't let you download it because it's not an authorized software. You need to override your security settings, something like that. I don't know. I don't use that operating system. But so it can be found here in this GitHub repository, or you can go to my awesome website, click on the free software, and then there it is. Links it to the same place, shilling my website, of course. Made. Um, anyways, so to download it, you would just go here to the newest release, which is lots of small improvements. Then you download the zip, and the zip contains like a Java file, and I'm pretty sure there are install instructions based on your operating system somewhere. Uh, it's not too hard. Windows, it's really easy. You just run the thing and you can create a shortcut or whatever. As long as you know how to operate a computer, you should be fine. So there it is, digital. So now that we have it booted up, I'm gonna be splitting this up into a lot of little sub chapters and probably time stamping it in thing. So depending on what you want to figure out, just jump there. Okay, so we're gonna start with the extreme basics, your essential components. So we have logic, which are, your ands, nands, ors, nots, and a lookup table, which we don't care about for now. And then the IO, which is your inputs and outputs. So the way it works, you can click there, drag, and place a component. And if you want to do the last component, you hit the L key on your keyboard. And I'm not pressing and holding. I'm just moving my mouse around freely and clicking to place down. And then we can drop a logic gate there. And if you can see there, these dark blue dots represent your inputs and the red dot represents an output. Digital is very finicky in that if you have an unconnected input, it starts freaking out, but you can have an unconnected output and it'll be fine. So like if I do, so what I'm doing here is I'm clicking, not holding, dragging, click, click, click to finish it. So if I were to try to simulate here by going to the simulation tab and clicking start of simulation, it's going to say error, nothing connected to input 2, open inputs are not allowed. That's what I mean by freaking out. It will very helpfully always circle the component where there's a problem. So now, yay, we're starting the simulation, but we have no way to read what the output's going to be. So we go to components, input output, and we have our output. Just drag another thing there, hit run. So the way this works, dark green represents a logic level 0, and as you can see as I mouse over it, it says the number 0. But when you click here, the light green represents a 1. So if I go about and click both of these, it's going to have a 1 there. Very simple, with the very basic logic gates. For some of you, that might not be enough. So logic gates are nice and all, but what about the more advanced features? Thankfully, in the library section, which on Mac, this might not have it by default, but there's always, a GitHub issue that you can look at that tells you how to resolve the problem. Thankfully for us Windows and Linux users, we don't run into those problems. So you have basically all of the 7400 logic chips you could ever want, and thankfully they're divided up into their functionalities rather than organized by number. So here we have the 74191, which is a presettable counter. And as you see here, this is the actual, let me pull up the data sheet for this. Yeah, this is the actual pinout. So you got your D. Oh, it does it by, here it does data 1, data 2, data, or here it does data 1, data 2, data 3, data 4, or data 0 through data 3, but here it does A, B, C, D. So, D1 is your B, Q1 is your QB, Q0 is your QA, etc., etc. So it follows the pinout as shown in the data sheet. And if you want to actually, if you've ever figured out what it is that's like going on inside of it, if you right click here, you can look at the included circuit. You can open it in a new tab, and this is basically what happens on the inside of this integrated circuit. These are the logic gate equivalents to the transistor topology of the internals, which is pretty nice. And then, this is a good format if you want to figure out how to like wire everything together so you don't like overlap. But this thing isn't really convenient. You got your inputs and your outputs all over the place. It's because that's how they built it. So you can right click on here, and under shape, you can actually hit simple. Click OK. And look at that. So you got all your inputs on one side, all your outputs on the other side, and what is that downside circuit? Oh, and look at that. So it actually has the thing that I showed you earlier, the internals, as a thing. I don't know why you'd ever want to use this. Layout. What the heck? I don't even know what this is supposed to be. Oh, I guess this is the layout when it, yeah, this is the layout of the internal circuitry. Layout, the dual inline, simple, and then default, and then default. And default is the dual inline packaging. So we have that settled. So now we are going to move on to the types of analysis you can do with a thing. So here, we go here, create our little AND gate right here. And to do analysis, you have to, emphasis on have to, name each port. So if we right click here, you say we're giving it a label. So if we name it A, name this B, and I think it allows some sort of like, some kind of like LaTeX commands, if you know what that is. So if I do O sub 1, yeah, it will do the subscript, and if I do caret 1, it will do superscript. I wonder if I do, yeah. So it's literally just like LaTeX where, subscript, superscript, whatnot, but we're just gonna name it O for now. And then think view, how do you fit to window? These are all your good stuff. Fit to window, hit F1. So, and now that we've named all of our ports, we can analyze it. So under the analysis tab, just hit analysis. And what this does is that it runs the truth table for the whole circuit. And I believe this can also be done for sequential circuits. I'm going to have to test that out later and show you guys. But yeah, so this gives the truth table. And of course, we know this is the truth table for an AND gate. If we swap this out for, let's say, an XOR, and we analyze it again, well, look at that. It's an XOR. And it tells you the equation down here. However, by default, it doesn't use that format. So if we go to, I think it's, yeah, edit settings, in basics, under format, by default, I think it's going to have this right here, this fourth one, where it's hard to read. And I'm more partial to doing this. You can choose this if you want A and not B, or not A and whatever. But here it's just ampersand is an and, exclamation is a not, hash is a or. Yeah. So that's pretty cool analysis. And you can look at the Carnot map. So if you go here, hit K-map, wow, look at that. There's the Carnot map. Pretty cool. And then you can create a circuit variant of this. So if you wanted to make this with just NAND gates, this is the equivalent of a XOR gate made of just NANDs. Circuit variant. And then if you want to make it to a device, which these are very interesting. So what these are programmable logic chips. This one is really popular, 22V10. You can translate it to Kupl code, which if you use the application WinKupl, you can program a JED file, or you can just straight up make a JED file. And I have no reason to think that these aren't working well. Or actually, I think in advanced, you'd have to give it a pin number first. So pin 1, pin 2, pin 23, and whatnot. So that's pretty neat. All right, so this next section is going to cover the different sorts of simulation, single gate stepping, and the measurement analysis. So the more well-versed people watching will recognize this as a static hazard glitch, which, seeing here, this Z, one branch of it only has 2 gates, while the other branch of it has 3 gates. So that means that because gates have delays in when they transmit, this path right here has a longer delay than this path, and that can cause the output, for even if it is a nanosecond, really, just to blip really quick. And a nanosecond, like, who cares? It's very short amount of time. And if you're just doing combinational logic and it's not interfacing with anything like sequential, yeah, who cares? But it's the 21st century. We have digital components well beyond 1 gigahertz clock speed at this point in time. It's very important. So, like, if this was sending, critical data to something operating at like 4 gigahertz or something, it could send the wrong data, the incorrect data, and it will actually, the processor will catch that, and then you could blow up something, kill somebody. It's tragic. Tragic. Why am I laughing? If we do an analysis of this, it's not gonna warn you like, yo, you screwed up. There's a static hazard glitch. And if we look at the Carnot map, you will know that to get rid of the static hazard glitch, you have to draw like a little circle there. But nothing here is really indicating that this has a static hazard glitch. If we do maximum path length, says the longest path has 3 gates, but it doesn't warn you that all the others do not have 3. So, and if we even do a simulation, it's going to show that everything's fine, nothing's really wrong. However, if we go to this simulation called single gate stepping, which you can get by just hitting G, and then if we step through each gate with V, we can do this sort of thing. So if we enter single gate stepping mode, and then we can show either measurement table or measurement graph, or actually both. Why not? Why not? So the way it works is if we have, I'm trying to think, I'm trying to remember. I'm sorry. Yeah. Oh, okay, so we need this break it, break. All right. So if we were to do now, if we do that with breaking, it's going to do that. However, you notice on the graph here, let me close it and reopen it so you can see it. I'm only hitting B right now, not V. So if we have this at 0, we make it go to 1, it stays. However, if it's going from 1 to 0, we have a little dip in F there, and then it automatically corrects itself. So let's see what's going on when we single gate step. All right, so we have this. What these circle means is that this is where the signal is right now at this point. So right now this is what's causing the delay, and this is what's causing the delay. If we step one more, that means this is getting the signal, but it hasn't recognized that, hey, both are high right now. Right now it only thinks that this input is 0, so they're both outputting a 0. And as we know, by the time this processes it, it's going to blip to be a 0, and then it's going to automatically correct itself that now that it sees this as a 1, and it goes back up. And this is very nicely done on this was useless. Let's close close that. But this is very nicely telegraphed to us, on the little waveform, which is a very, very helpful tool because nothing else catches this. And it's a very good visualization of what's really, going on. Books can explain it to you in words, but it's very nice to have a sort of animation that you can use to check with. Very cool. So now we're going to look at synthesis. So, you can obviously make your own, whatchamacallit, random sort of deal. And then it gives you the thing there. And then we can create a circuit, right, like that, so we can see the circuit we've created. And it's a very easy way, instead of having to, draw your own, digital logic. I know it makes you think, but once you've done all the thinking, eventually you're gonna have to be like, oh, I just want to get this over with. Good God. So this is a good way to just put in your truth table and then automatically generate a circuit for yourself. And if you're so inclined, you can do circuit variants. If you want to do, this is for sequential logic. If you wanted to make something with a JK flip-flop instead of D flip-flops, you can do that. And at most 2 inputs, 6. And a lookup table, which is just this thing, and it's neat. So this is the whatchamacallit, the data, which I might explain or I might forget. So so that's all fine and dandy. Now we're gonna move on to sequential logic, which this does really cool sequential logic stuff. Or actually, first of all, scratch that. We're gonna go through each component. So we have all of our logic things and then our lookup table. That's self-explanatory. Explanatory. Sorry. Outputs. These are cool because you can actually change the amount of data. So, you can make data being a bus where one wire represents 4 bits. You can change it up to, well, it gives you a pre-selection of 8, but you can just type in like 32 and it doesn't care. Now, the way it's displayed, you can actually change that. So, by default, it's going to do, I think it actually does a hexadecimal by default. It's not binary. I know that for certain because, wait, let me change this to 4 bits. A little experiment here. 4 bits. Yeah, by default it's hexadecimal. So that doesn't matter if you're working with 1-bit stuff, but if you wanted to, display the binary for a thing, you'd have to change it to binary, and it does a bunch of other stuff: decimal, signed decimal, octal, ASCII representation, and a bunch of fixed point and floating point arithmetic, which I'm not gonna get. I don't even understand most of that stuff myself. I don't really care because I prefer RF, but that's a cool little deal you can do. Input, I showed you that already. It's basically the same as the output. You can change the number of bits. Oh, and you can change the default value of the input and a 3-state. So the way that, oh, hell. All right. So the way the 3-state works is that you have your 0, your 1, and then you're not connected at all. This is your high impedance input, which it represents neither a high nor a low, and those are used really in, I think, tri-state buffers. Does this have a tri-state buffer? Yeah, here we go. Change this back to single state. And you can, oh, fun other hotkey thing, hover your mouse over something, hit Q, there you go, you copied it. You've copied all of its properties as well. Just show this off real quick. This is an example. So this gate is not activated, it's not going to transmit anything. But if you do that, it transmits tri-state buffer in like 20 seconds or whatever. I'm getting lost because I am nut job. Let's see here. All right, buttons. These are cool because when you hit the button, it's not, oh, geez, it's not like the inputs where it does it. This is like press and hold. The fun thing is that you can give it a label and then you can map it to keyboard, or you can change the active low. So if I give it, I think, letter L, hit OK. Oh, I have to map to keyboard first. Push play. I am hitting the letter L on my keyboard, and look at that. And you can do the same thing with arrows. I think if you type right, if I hit the right arrow, yeah, the right arrow on my keyboard. And I don't know about control. No, doesn't work. Probably because those are modifier keys, but you get the point. IO, dip switch. What's there to be said? It's a dip switch. Yeah. Oh my god, why do I keep doing that? Hit that, click it. Wow, fascinating. The thing I don't like about this though is that you can't have like multiple bits or as a one continuous block. You can do it. You'd have to like do that, stack them. That's dumb. I wish they would change that. Probes. This is to I don't know why you wouldn't just use an output rather than a probe. A measurement value can be shown on the data. Beta circuits. Who cares? This is, remember in the earlier section of the static hazard glitches where I showed you the measurement graph? I am 60% certain this is like the exact same thing. You can read the description, pause these and read the descriptions. I'm not going to pad out the length by reading this. Displays, here you go. So you can have your 7-segment display. Unfortunately, you cannot configure this to where it has a favorable sort of deal with the inputs. the way to do it, you hit common connection and do it cathode or anode. And of course, everyone knows cathode, you ground it, anode, you power it. I apologize for the hiccup. And this one appears, and it is, if you hover over it, common anode, A, B, C, D. I'm going to set up a circuit real quick. Okay, back. And I am glad I decided to use this circuit as an example because I forgot to go over this one because I am an idiot. So if you, this is the clock. If you right click on it, you can start a real-time clock, give it like whatever hertz you want. The maximum, I don't even know what the heck that is because this is 50 kilohertz. Let's go with 2 because why not? So these are the 7400 logic chips, and then that's a 7447. So if we just let it play, yay, we're counting. That's what it looks like. There's the special ones for the higher than 9. It loops back around. Cool. So yeah, there's that one. And then there's other displays. You can have 16 light bulb, LED matrix for like really cool advanced stuff. People made really crazy stuff in here. Rotary encoder, whatever this stuff is. Peripherals. Believe it or not, you can have a keyboard like interface in here where you can type stuff. A terminal. You can write ASCII characters into the terminal. Telnet. I don't know what Telnet is. I think this is like actually some sort of, you can receive data from like the rest of your computer. This simulates a VGA monitor. And then this one it's like a MIDI system, which is I believe it's an electronic format of playing music. And I know that there's one example circuit in here where they play a Michael Jackson song, which is pretty cool. You might notice here, like, what are these right here? So if we go into our next category, we have grounds and supply voltages. I hope you know what those are. Constant values, they basically do the exact same thing as supplies and grounds. Or I don't know, can you set these to be impedance? Or I guess it's better because you can do like multiple bits and whatnot. But I don't know. Can you do Z? Yeah, never mind. You can't. You can't do high impedance. That's silly. But going here, a tunnel. All a tunnel does is that if you give it a label and you connect it to one wire, you can have another tunnel with the exact same name going to another. It's basically a way to connect wires without actually having to connect them. Sort of like a net name in like LT Spice or something. You can name a net and then you can have like one part of it going. It's cool. Uh, Splitter merger. What this does, this takes in a bus or this takes in a bunch of wires and then it either splits a bus into individual wires or merges wires into a bus. So the way it works, I always screw this up. So it's the number of bits star the number. So that means if we wanted to take in a bus of 8 bits and split it into 8 wires, we do that. And look at that. Very cool. And I believe it uses, I think it's called Big Endian, where bit 7 is going to be the leftmost, most significant bit, while bit 0 is the least most, or least significant. I believe. Let me, we can check that real quick. Make it small shape. Give this 8 bits. Play. Yeah. Yeah, it's Big Endian. Very cool. delete this stuff. Going into more components, wires, drivers, invert select. This is what I was showing you earlier with the high impedance stuff. A delay, just do like propagation delay and whatnot. Pull up resistor, pull down resistor. If a net is in a high Z state, this resistor pulls the net to high. I can't think of a case in the simulation software where you'd need it. In real life, you'd need this if you have like an open collector output on a IC, kind of like I believe 7447s are output collectors. I don't know. And then not connected. I've never used this. A component can be used to set a wire to high Z if a. Oh, so this is just. Oh, this is the con. So remember how I was trying to do high Z constant? Well, there it is. Multiplexers, demultiplexers, very cool. So you can have the number of data bits per input. So if I change this to, I'm an idiot, I hit cancel. If you change this to 4, it's going to be that, but I believe if I hover over, no, it's not going to tell me how many bits. But if I change the number of selector bits to 2, it's 4 because 2 to the power 2, 3. There's 8 of them. It's cool. Flip selector position. I think that moves that to the top. That's nice. Plexers, demultiplexer, decoder. This is like the decoder encoder stuff. Very basic circuits. Priority encoder. This just has it. It's very nice. Components. Plexers. Alright, now we move on to the sequential logic. Hooray! We're finally here. So, everybody should know, at least if you're watching this far in the video, how flip-flops work. Pretty simple. They hold data for however many clock cycles until it needs to switch. It's a type of memory, very basic memory. And then we have different types of memories, RAMs, EEPROM simulations, all this jazz. You have your basic counter, arithmetic, adders, subtractors, multipliers, dividers, barrel shifters, all this stuff. It's very fun to play around with. You have different switches. You can even make like discrete stuff out of FETs and diodes. Oh, these are fun. Transmission gates. I believe, don't quote me on this, in real life, transmission gates can be used to like send analog signals back and forth. I think there's a IC in the 4000 series that use these. It's kind of like a multiplexer for analog signals. And then miscellaneous, we got VHDL Verilog, which is going to be its own section. Power. I think these are mainly just used if you like make your own 7400 circuit library. Bidirectional splitters. They go either way. Resets, breaks, stops, test cases. Of course, your libraries, all your stuff, your EPROMs. Never use these. I've never used that. I've never used that. Alright, so as I said earlier, everyone should know how the basic flip-flops work, but making state machines, especially discretely without HDL, is a pain. I know, because I've done it. However, this mitigates your pain a lot. If we go into synthesis, if we go to new, we can actually make a sort of sequential thing. So if you want to, I'm using an example I have in this book right in front of me, Digital Design Practice Principles and Practices by Wakerly. So I'm going off an example in there just to demonstrate it to you. But this is going to be a real simple state machine. It has basically it's a 2-bit state machine. It has an input and then it has output. So like you input stuff and you output it. So we create a new thing, sequential, give it 2 variables, then we can edit it. We can add an input variable. We can, we can rename it to enable as it is in the book, new, or not that. And then add an output column, rename it to, you have to right click it. What is this called? Max in the book. All right. Set all to 0. There we go. Hooray. So I'm probably gonna superimpose the image off onto here so you can see what I'm looking at. So if it's 0, 0, 0, it's 0. If it's 0, 0, 1, this guy, Q0, becomes a 1. If it's this one, whoops, I'm dumb. Here, because that's... So if the current state is 0, 1, it stays on itself. All right, next guy, it stays on 1, 0. Otherwise, it goes to 1, 1. If it's on 1, 1, it stays on itself. Otherwise, it wraps back around to 0. And if it's 1, 1, 1, the output is also that. Very cool. I don't know if you can view Carnot map. It's weird. So if we create circuit, this is what it's going to look like. And if I'm looking at the actual, I'll put the circuit figure there. I'm inspecting it currently. It's a little different because these use a different sort of deal, but this looks to be about the same. And then you can further analyze this, I think, by doing finite state machine. Damn, that's unfortunate. So I can't like create my own finite state machine, but if I run this, so if it's 0, 0, stays there, stays on itself, moves to the next one, moves to the next one, max, hooray. It does it. It does it perfectly. So as long as you have the state tables for your design, you can implement the circuitry using this and test it. It's very cool. Now, this is just like you can't like create it from your design. You like make it manually. The final thing we're going to look at is the VHDL sort of deal. So the way the VHDL works, you need well, it's both Verilog and VHDL, but I like VHDL. So if we go to settings and we go to advanced, what you need to download GHDL. GHDL is pretty easy to find. You just type in GHDL and it will do that. You need to, if you're on Windows, just download the zip. If you're on Mac, do whatever. I don't know what the heck goes on that computer. If you're on Linux, like myself, I believe. Yeah, look at that. It's in my the repository for my operating system. So you put the path to the executable in here. So that's where mine is. And if you're in like Windows, it would look something more like that. That's how that works. So we go to miscellaneous. VHDL/Verilog. You can either input a file or you can just do an external sort of deal. So let's do external because that's easier to see. So here's our little thing. On our options, don't change this because 2008 is the better option. Change the width. I don't know why they defaulted at 3. It should be more like 7. And then in the application, in this drop-down box, select VHDL if you want to do VHDL. So let's go here. All right. We do not care. So just select all this stuff, copy it, and close this. Screw you. Control V to paste it. There you go. You just put in VHDL. It'll check the syntax, and if nothing's wrong with it, it'll be like, hooray, you've done it. A, B are your inputs. O, R is your... Wait a minute. This isn't a full adder. What did I do? What am I doing? We don't care. It's capital G. What am I doing? I'm such an idiot. V, capital G. There we go. There we go. That's an actual full adder. So paste that there. Check it. Hooray, it works. And this basically works in a way where you can just do your outputs there. And then your inputs here. And it will work exactly as described in the code. So click play. You know, your full adder, the way it works is that the sum is an XOR gate, and then, oh wait, that would be a half adder. It's something, so there. And then if you do this third one, hooray, you carry in, like, 1 plus 0 is 1. 1 plus 1 is 1, 0. 2. 1 plus 1 plus 1 is 3. Pretty cool. Alright, that's basically it for the VHDL. You can type like insanely complicated code. Let's see. Let's go up. Counter. Let's get this guy. Copy. So, because this is sort of like a test bench, you actually do need to declare signals with initial values. It's very stupid, but it's the way it is. So that's why I'm giving it an initial value of all zeros. Because if I don't, what it starts at, I think it starts with like U uninitialized, and it just doesn't know what to do from there. So hit OK. What? Oh, check. Okay, there we go. So Q is going to be 4 bits, and let's just display it in decimal. We got our clock here. Let's make it a 3 hertz clock, and then we got our down up pin. So if it's grounded, we're going to go up. If it's powered, we're going down. Or the other way around, actually. 3, 2, 1, 0, 15, 14, 13. Switch it. Very cool. Very awesome. That's how you do the VHDL sort of deal. So remember, you need to actually download GHDL to get this functionality. Alright, so, and then I guess we can look at some discard changes. I don't care. Where's the example projects? Where are they at? I'll find them eventually. Hold on. Yeah, here we go. Examples. This is a HDL example right here. Basis 3 light chase. Oh, this is one where you can actually export this to a basis 3. There's a tool chain configuration in this thing. What is it talking about? What? Oh, I guess this is something you have to like download. Vivado, create a bitstream. That's pretty nuts. Yeah, this thing does a lot. Let's look at other stuff. 7400, we don't care. CMOS, oh, finite state machines. I think we'd have to open that in. Let's go to finite state machine file, open. There we go. Here we are. Hey, look at that. It's a traffic light. Cool. But we care about this right now. So, generic barrel shifter. What? No, not mess with that. Oh, here we go. More hazard glitches. So simulation, single gate stepping. Here we are. So if we do this, but if we do that, wow, crazy. And this is using the data graph component instead of this one. I prefer this one. But yeah, I might as well explore this one. Maximum amount of steps to show 19. That's how that works. Open. Oh, here's an oscillation. So this is an oscillator. Single gate stepping. If we do that, it goes forever. If I tried to end it, error calculating step, logic seems to oscillate. So it will warn you if you've accidentally made a ring oscillator or something like that. And I think even if we try and like play it, yeah, very sad. File. Alright, did hazard, miscellaneous. Oh, that's the fun stuff. We're gonna look at it earlier. This is the stuff with an NMOS. You can make an inverter using NMOS. That's how it is. It's an inverter. Oh, and these tests, what they are, they basically you give it like expected stuff, and it will verify all the tests passed. Hooray! Yeah. Here is XOR. Cool. Very cool. Open. Thing. Is there like a PLDs, gal 22. Alright, so this is I guess how a gal is made. This is what they look like on the inside. I'm not gonna mess with this. Wired ore. Oh, I guess these use diodes. Yeah, this is the type of logic. Pretty cool. Go here, processor, HDL example.dig, pin numbers. Oh, this is another thing where it's just like whatever. Here, a VGA example. So here's a VGA. Is it not going to open it? Probably because I don't have a monitor set up. Whatever. Or wait, maybe it did open and I'm just stupid. No. Should be opening. Open. Alright, here we go. Sequential. Here's Conway's Game of Life. Pretty neat. These are made of like if I'm able to select the stupid LED, yeah. This is made of like a custom component and stuff, and I better get out of here before I screw anything up. Go, these are different things. Now the miscellaneous telnet. What does this do? Enter text. I don't know. Did something. Debug example. I wish this came with documentation, but here we go. Here's a Medi. Billie Jean.